I'd like to introduce you to Kyle Salois from Colorado State University. He'll be talking about inequality of a class of Schur-Q functions.
All right, hi everyone. Like was said, my name is Kyle Salois. I'm from Colorado State University. I'm going to be talking about work that I started last summer with my advisor, Maria Gillespie, and it's sort of turning into this master's project. Feel free to interrupt me at any point if you have questions or have some sort of clarification you want made. I love for this to be more of a conversation than just me talking at you. But otherwise, we're going to talk about these sort of Schur-Q functions. So I'm going to introduce sort of what Schur-Q functions are, how we build them up. I'm going to talk about how we can describe sort of skew Schur-Q functions in this Schur-Q basis. Okay, so starting with sort of our motivation. So a basic problem in symmetric function theory is, well, the normal Schur functions, so non-shifted, non-Q, arise in a bunch of different areas: representation theory, algebraic geometry, and sort of these Littlewood-Richardson coefficients, which is how you can sort of describe a multiplication of two Schur functions arise in these fields. And so you can ask different types of questions about these, including like, when are two Schur functions equal? If two Schur functions are, say, indexed by different skew partitions, if they're equal, then that tells you a lot about the Littlewood-Richardson coefficients, and so it can be helpful in those fields. So we can extend that problem by looking at this different class of symmetric functions. So there's a basis of the ring of symmetric functions called omega, which is indexed by, or generated by the odd degree power sums. And one of the bases for these are the Schur-Q functions, similar to the original Schur functions. And these are related to shifted partitions, and they also arise in representation theory. And so sort of the same problem, how can I understand when two of these are equal if they're indexed by different, say, skew partitions, is a question you might want to ask. If you're not familiar with shifted partitions, it is essentially a normal partition where you're sort of shifting over each row by one more than the last row. So on the left here, we have the example of the shifted shape 6, 4, 3, 1. So I have 6 boxes in the first row, and then I move in one, I sort of indent it, 4 boxes, and then indent 3 boxes, and then 1 box. And likewise, just like in normal partitions, we can take skew partitions. So on the right, I have this shifted skew shape. There's lots of S's in this talk. 6, 4, 3, 1, skew 4, 3, where I've removed the first 4 boxes from the first row and the first 3 boxes from the second row. So what are these Schur-Q functions? Well, if I have some shifted diagram D, which could be either a straight shifted shape or a skew shifted shape, the Schur-Q function is given by Q sub D as the sum over all semi-standard tableau T of the shape D of this monomial x to the T. If you're familiar with symmetric functions, you know what this x to the T is. You just say, you take the weight of the content of whatever your filling is. Now, semi-standard has a slightly different definition in the shifted partition world. So we've extended our alphabet to include not only the natural numbers, but also their primed versions. And we consider the primed versions sort of less than the original version. So we have the ordering 1 prime is less than 1, which is less than 2 prime, and so on. Just like in regular partitions, the filling has to be weakly increasing across rows and down columns, with the additional thing or requirements that sort of I can't repeat primed entries going across the rows, and I can't repeat unprimed entries going down a column. So this is an example of a filling of the shape we saw earlier. You'll notice in the top row, I'm allowed to repeat the unprimed 1s, and in that column of 3s, I'm allowed to repeat those 2 primed 3s. But all of the columns and rows are still weakly increasing. And then if you look at the weights, since there are 4 1s in the filling, this sort of corresponding monomial term has x1 to the 4th. There's 3 2s, so x2 cubed, and so on. So you take the sum over all such fillings. Okay, a specific type of sort of shifted skew shape that has some prominence are called ribbons. So this is a shifted skew shape whose diagram does not contain a 2x2 subdiagram. So it doesn't contain a little 2x2 box. In other words, it's a long and skinny ribbon. So ribbons are cool because in understanding equality of regular Schur functions, I believe they sort of had this useful technique of decomposing your large shift or large skew shape into sort of a union of ribbons. that was sort of helpful. And so there was this paper put out in 2009 by Farzan Bearcat and Stephanie Van Willigenberg that was sort of like, well, maybe ribbons will be helpful when looking at the Schur-Q functions. And so they determined this theorem that sort of says, if I have two diagrams that satisfy these conditions, then their corresponding Schur-Q functions are going to be equal, which was really cool. So for example, if I have these two ribbons in the top diagram, their corresponding Schur-Q functions are equal according to this criteria. It's not super important what the criteria is for the sake of this talk. What myself and Marie Gillespie noticed was even with these sort of simple ribbons that are sort of equal to each other, and sort of the way of putting together sort of ribbons and composing them does not extend once you are past the ribbon case. So in this below diagram, the only thing we've done is move that lax box over by 1. It sort of breaks the fact that it's a ribbon. Now we consider it a ribbon plus a box, because if you take away sort of a maximal ribbon from the inside, you're left with a single box. Turns out the corresponding Schur-Q functions where these shapes are not equal. And so that's kind of evidence that maybe ribbons are not the sort of standard approach. Perhaps they don't tell us everything we need to know about Schur-Q functions. So here's our sort of more rigorous definition of a ribbon plus a flap. So this is a ribbon, and then you add a new row on the bottom and you put a single box in it, and it must be connected to your old shape. It's pretty straightforward. So here's an example of a skew shape that is a ribbon plus a flap on the left. And then this thing that we're calling an antipodal reflection on the right, which is where you reflect the shape through the northeast southwest diagonal. So sort of the other diagonal than you're used to with transposing partitions. It turns out that if you have a ribbon plus flap and you do this reflection to it, you'll also get a ribbon plus a flap. In actuality, any shifted skew shape, this reflection maintains that it is a shifted skew shape, which is pretty cool. Okay, so the conjecture that the rest of the talk I will be presenting evidence towards is that if we have two different, or actually if we have two ribbon plus flap shapes of size n with equal Schur-Q functions, then they either have to be the same shape or antipodes of each other. So it turns out the function for a given shape is equal to the function for an antipode, but our conjecture is this is the only time where they're equal to each other. So unlike the case where we're just in ribbons, and we can get a bunch of different ribbons that sort of have equal Schur-Q functions, our belief is that even if you just have a very simple ribbon plus a flap, like sort of the next step in complicatedness, you can't get equality sort of in any non-trivial way, which is sort of interesting. So what is the technique we used here? So in the ribbon paper, they were sort of looking at sort of building up these things inductively, looking at taking your shifted shape and sort of translating it into a non-shifted shape and sort of examining the shapes in that way. But we now have this new machinery that sort of helps us examine these functions a little in a different light now. So a theorem in 2017 says that given a shifted skew shape, the corresponding Schur-Q function, Q lambda skew mu, can be written in terms of the straight shape, the straight shifted shape Schur-Q basis, according to these sort of F coefficients. So if you're familiar with normal Schur functions, these would be the Littlewood-Richardson coefficients. And so these new ones we say are a Littlewood-Richardson type coefficient. The exact number is the number of ballot fillings of your large skew shape with whatever your new content is in a ballot way. And so what does it mean to be ballot? Well, again, we need semi-standardness. So that's that primes and unprimed entries business. The tableau has to be in canonical form, meaning if you take the reading word, so left to right and bottom to top, the first sort of entry of each number must be unprimed. And then lastly, we have this lattice walk condition where, so I take sort of I and I plus 1, and I look at the corresponding lattice walk, and it has to end on the x-axis. So what is this lattice walk condition? Well, again, it's not super important that you know the full definition, but in general, if I'm comparing, say, 1 and 2, the smaller number, so 1, is roughly moving down and to the right. And the larger number, in this case 2, is moving up and to the left. And so if I want to follow my lattice walk and make sure it ends on the x-axis, I have to have enough smaller numbers following each of my bigger numbers. And this kind of corresponds to the ballot condition for regular Schur functions, where I have a sequence of 1s and 2s, I pair them up, and I have to be able to pair them up with this sort of parenthetical thing, or you can think about sort of lattice walks that stay above the line y equals x. There's a lot of ways to formulate it, but this ballot walk definition is similar to that one, except now we have to sort of look at primes and unprimes and all that stuff. I will pause here briefly for questions before I start talking about the results. So if anyone has any questions, now would be a good time to ask them.
Do the ballot sequence correspond to Yamanouchi words?
Yeah, so that's sort of the correspondence we have here. So this is almost it's similar to Yamanouchi, right? But it's not exactly the same because obviously our alphabet is slightly different.
Okay, thanks.
But yeah, that's sort of the inspiration and definitely a good place for your intuition to be at. Okay, so what have we shown? Well, first of all, if we have ribbon plus flap shapes and they have a different number of turns, so a turn is a place where I'm going to the right and then I turn to go up and then I turn to go right. Those are all turns. Then the corresponding Schur-Q functions are different. And the way we can do this is by looking at a single coefficient in the expansion. So the coefficient where I have 2 2s and the rest 1s in my filling. So on the left here, I have a single turn. It's going to be the case that in all of these fillings, one of the 2s has to be sort of down in the lowest box in the flap. And so we only have one other 2 that we can work with. I put a star on this 2 to indicate that it can be either primed or unprimed. And it turns out those are going to be the only ballot fillings of this shape because right, the only other free entry per the semi-standardness would be the 1 above the 2, or the 2 star. But that can't be primed because of the lattice walk condition. It wouldn't bring us back down to the x-axis. So we need an unprimed 1 following my 2s to bring us back down. This should be your intuition. So in this case, the coefficient is 2. In the next shape, I have 2 turns. My coefficient is going to be 4 because I still have the same freedom on that 2, but I also have freedom on the 1 above it because I have an unprimed 1 later in the reading word. And then lastly, if I have 3 turns, for example, I have the same 4 coefficient on one of the shapes, but now I can move the 2 to another corner and still be semi-standard. And it turns out we get 2 more of these ballot fillings. So for a total of 6 for the coefficient. So these are all different. This argument generalizes. It's pretty cool. So then I have distinguished different numbers of turns. So maybe now my next step is to look at a single number, or like I pick a number of turns and I want to distinguish all of the functions within that. So here we're just looking at shapes with 1 turn. So if I have 2 shapes that are ribbon plus flaps with 1 turn, they have different heights. So 1 turn is sort of a row and then a column, and that's it. So if their columns have different heights, then the corresponding Schur-Q functions must be different. So like before, we were looking at sort of these coefficients, but instead of looking at a single coefficient, now I'm looking at 2 whole families of coefficients. And so we can prove something about these coefficients to draw this sort of coefficient table. So here I'm looking at all of the size 10 ribbon plus flap shapes with 1 turn. H represents the height of that final column, and sort of the rows to the left tell you what is the coefficient of that basis element in that expansion. And so these 2 families are really cool because the first one sort of pairs them up. So for example, the Q73 component pairs up height 1 and height 6 because those have sort of maximal coefficient Q82. But then the other family of coefficients where I have a single 3 are actually going to distinguish between those pairs. And so as a result, all 6 of them are different from each other. And all of this is sort of using the same argument we used in the last example with the pictures, where I sort of first fill it in via semi-standard, and I have to examine all of those to see which of them are ballot and count them that way. Our final result is now looking at shapes with 2 turns, so a row over, a column up, and then another row over. And now my column height is 1, 2, or 3. So I either go up 1 box, 2 box, or 3 boxes. different first row lengths, so they're not the same exact shape, then once again, sort of these are going to be different from each other. And this argument follows the same argument as the last one, where I am sort of examining two different families of coefficients. One of the families sort of pairs these shapes up, and then the other family distinguishes between those pairs. So that's the work we've done thus far. Our future work is to attempt to generalize this argument. Already with sort of height 1 into height 2 into height 3 cases, sort of what these coefficients are doing gets really unwieldy. Even in height 3, you have like 5 different cases to say when is your coefficient 0 or 2 or 4 or 6 or 8. And so we want to find a way to sort of make this argument more abstract instead of actually going into all of the deep case work. Other than that, I'd like to thank all of the organizers for letting myself talk and everyone else who's given amazing talks. And thanks to everyone who showed up and listened.
Okay, let's thank our speaker. Okay, any questions for Kyle? Just call him out.
I had a question about the connection to representation theory of the symmetric group. Can you say anything about that?
Yeah, so I have not done too much research into that as of yet. That's sort of a project for me over the summer because we sort of jumped into the symmetric function theory part. And now I have to sort of backtrack and see the motivation. For normal Schur functions, if you look at the irreducible representations of the symmetric group, it turns out that these Littlewood-Richardson coefficients sort of come up as the characters or irreducible characters of these representations. And so a guess would be that the Q functions show up as characters of the projective representations. But if we're being honest, I don't even know what a projective representation is.
Thank you.
I have one question. The Schur-Q functions are symmetric functions, right?
Yes.
So do you gain any information if you look at quasi-symmetric expansions? So can you write the Schur-Q function as sum over some kind of standard shifted tableau with the quasi-symmetric expansion over the descent set, something like that?
We have not looked at that. So the only other basis we have looked at of the sort of omega subring is the just the normal monomial basis. So instead of looking at only semi-standard fillings, now you're just looking at sort of all possible. Are they still semi-standard? I don't know much about this because everything we found by looking at the monomial basis, we also found by looking at the Schur-Q basis. So the answer to your question is no, we haven't looked at that yet. We definitely could.
Okay,
keep that in mind. So thank you.
And maybe one more question, because I know that there are crystal-like structure exists for the ribbon tableau, or what do you call them? Your tableau, the shifted tableau. Do you get anything out of this?
So this is actually where the definition of this sort of Littlewood-Richardson type coefficient came from. So Marie Gillespie, Jake Levinson, and Kevin Prabhu, in their paper, they developed a crystal-like structure. So I think these are related to type B sort of Lie algebra things, but again, that's not something I've looked into yet too much. And so the hope was that you could find some sort of type B crystal that sort of decomposes in the same way that the type A did for the Schur functions. It turned out that they didn't quite find that. They found sort of a doubled type A situation where all of your crystal operators sort of affect either the ones or one primes in this sort of double E crystal way. But using these sort of pseudo crystals is how they found the representation of these coefficients and how we got a combinatorial definition for how we can use those.
Okay, thank you.
Okay, so it seems like there may be a lot of questions for Kyle, but just in the interest of time, let's thank Kyle again.